In this video, we are going to be going through the Unit 7.6 VSEPR Quiz Review assignment on Quia. This assignment is to be completed on Wednesday 325 and Thursday 326. Before you start, you should have out your molecular geometry summary sheet, so I have a picture of it on here on the right, and you should also have out a periodic table. For our first question, we need to fill in the Lewis dot diagram for CO3 with a -2 charge. And then this Lewis dot diagram is going to be used to answer the next 6 questions. We're going to start off with a carbon atom with 4 valence electrons, and then we have 3 oxygen atoms. So I'm going to include one on the left, one on the right, and then I'll put one on the bottom. Now, I also do have a -2 charge here, since this is an ion. That means that I have 2 extra electrons that could be placed anywhere that they're needed. So I'm going to put one on this oxygen. I'm going to use X's here just to show that those are our extra electrons, so you don't lose track of them. And that completes the octet for this oxygen on the right and this oxygen on the left. The carbon here in the center and the oxygen over here both only have 7 electrons. So what I'm going to need to do is take those lone electrons and place them in the center in order to make a double bond. So essentially what this is going to look like is a carbon double bonding to an oxygen, which has its 2 lone pairs, and then the 2 single bonds to oxygens, which each have 3 lone pairs. So that is my Lewis dot diagram. Now for the 3D sketch for this one, I have 3 bonding directions and no lone pairs on it. So I'm going to have my central atom. I'm going to have one bond which is going away, one bond which is in the plane of the paper, and then one bond which is coming out towards me. So if you're not familiar with actually drawing these 3D sketches, the dashed line means that your bond is going away if it is just a normal line that's in the plane of the paper, and then any thicker line is coming out towards you. So now that we have our pictures, we're going to attempt to answer each of the questions. For our first question, we are asked how many bonding directions are on that central atom. So there were 3 bonding directions. Remember, a double bond still counts as a single direction. How many lone pairs are on the central atom? Well, on the actual carbon, there was 0. What is the electron geometry? Now, at this point, you will look at your molecular geometry sheet, and you know that there were 3 total electron groups, so I'm going to go across that row. The electron pair geometry, or electron geometry, is labeled as trigonal planar. So I'm going to select that choice here. What is the molecular geometry? If I continue across that row on the VSEPR sheet, I had 3 bonding directions and 0 lone pairs, so that means that it is going to be trigonal planar again for the molecular geometry. Those 2 names do not always match up. They typically only match up if you have 0 lone pairs. Now for the approximate bond angle here. This is going to be 120 degrees. This is also something that we can get straight from that molecular geometry sheet. And now for the polarity of the molecule. Now for this one, we're going to go back to look at our actual picture. Now this right here, this is actually a resonance structure. So this double bond is evenly distributed between all 3 of these locations. So we have our picture here, and because we have the same oxygen on all 3 of these ends, this is going to be completely symmetrical. And since it is symmetrical, that makes it nonpolar as a molecule. So even though this has 3 polar bonds, because of the connection between carbon and oxygen, it is going to be nonpolar overall. Number 7. Which of the following molecules can participate within hydrogen bonding? Now, in order to have hydrogen bonding, you have to have a few criteria met. Your hydrogen atom must bond to one of 3 different atoms. It could bond to a fluorine, an oxygen, or a nitrogen. They have to be extremely electronegative. You also have to have a lone pair of electrons which is going to be present. So I'm going to look through each of my choices here and see if I can eliminate any. This one, phosphorus is not one of those 3 super electronegative elements, so I can eliminate that. Nitrogen is one of those super electronegative elements, but there's no hydrogen here, so it can't be that one. Well, clearly it can't be all of these choices if I just eliminated the first 2. For the final choice, carbon and hydrogen, that combination is not enough of an electronegativity difference. The best answer here is going to be the HF. And if you were to actually draw this out, this fluorine does have lone pairs around it as well. So that would be your correct answer. For the next one, which of the following molecules have London dispersion forces? Now, London dispersion forces are the weakest of our intermolecular forces. These forces occur from the random assortment of electrons within a molecule. At any given moment in time, if I draw out something like my CH4, which is the first choice there, we show these electrons within these bonds and everything looks like it's evenly spread out, but electrons are actually moving around within the molecule very quickly and randomly, and at any given moment in time, maybe there's more of the electrons that are towards the left side of the molecule as opposed to the right side. That would make one end partially negative and one end partially positive. It gives you something called a temporary dipole, which allows these molecules to stick together a little bit because they have this positive and negative charge. Now, London dispersion forces are present within all molecules, whether they are polar or nonpolar. For nonpolar molecules like this one right here, that's the only intermolecular force they have. Something like water, which is our next choice, water can also participate in hydrogen bonding, which is a much stronger intermolecular force. What we had up here, it has that H to O combination plus the lone pairs. But the London dispersion forces, they're present within all molecules, so we would say that all of these choices have London dispersion forces. You want to be careful about how the question is phrased. If I asked you which of the following molecules only has London dispersion forces, well, then you would have to pick a nonpolar molecule, which would apply to CH4. It would also apply to the CCl4 here, so it would have to be a multiple select question if I phrased it that way. All right, for our next question, which of the following molecules have dipole interactions? Now, in order to have a dipole interaction, that means it has to have 2 poles, because that's what a dipole means, and they have to be permanent dipoles. That means that we are looking for polar molecules. So in order to answer this question, you would have to think about what the structure for each of these would look like. If I have the CF4, I have 4 single bonds going to each of these fluorines. Now, while this is a polar bond, this is not a polar molecule because this is completely symmetrical. So since this is a nonpolar molecule, it cannot have dipole interactions. So it can't be that choice. If I drew the CF3 with the Cl, it's the same general shape as a tetrahedral, but this time a fluorine is not going to cancel with the chlorine. That makes this a polar molecule, which means that yes, it could have dipole interactions. But let's look at the rest of the choices. BCl3. So for this one, I would have 3 chlorines, and there's no lone pair on the boron. This would be an exception to the octet rule. So because of this, it is completely symmetrical, whether you cut through any of the bonds, which makes it a nonpolar molecule. So you can eliminate that. And then finally, you had Cl2. So if these 2 chlorines are bonded to each other, that is definitely a nonpolar bond and a nonpolar molecule. They're going to have the same exact desire for electrons, so that doesn't make sense either. All right, question 10. Which of the following, which type of intermolecular force is the strongest? Now, ionic bonding you should be able to eliminate right off the bat because that is not even an intermolecular force. That is a type of bond which we could refer to as an intramolecular force. So then we're down to the remaining 3. London dispersion was the weakest. Dipole interactions is somewhere in the middle. Hydrogen bonding is going to be the strongest. So that's just a fact that you would have to know from your notes. Alright, 11 and 12 here deal with hybridization. So if you did not watch the notes video, which was assigned within the first week of our flexible instruction, please make sure that you go back and watch that because we did not cover the hybridization within class. The first thing you would have to do is know what the structure looks like for carbon dioxide. So we're going to have a double bond on either side of the carbon. We have two bonding directions here. Now, in order to have carbon bond within these two directions, I'm going to need to have two orbitals come together and hybridize. You're always going to have at least one s orbital, or should I just say one s orbital, because you'll never have more than one. You're going to need at least one p, and you could need more. Well, if I have one s and one p blending together, that gives me my two potential hybridized orbitals, or two bonding directions. So that's what I'm going to have here, sp hybridization. If I look at something like BCl3, this one has three bonding directions. And there's no lone pairs on the central atom. Well, if I'm going to have these three bonding directions, I'm going to need an s orbital, and this time I'm going to need two p orbitals, because 1 plus 2 equals my three potential bonding directions. So this one is going to be Sp2 hybridization. How many p orbitals are used within the creation of an sp3 hybrid orbital? This is actually an incredibly simple question, so do not overthink it. You can see that there are three p orbitals here within this hybrid structure, so you must have had three p orbitals in order to make that happen. So that's as simple as this question is. If I asked you how many p orbitals were used in sp2, it would be 2. If I asked you how many were used in sp, it would be 1. 14. Which type of bond is a result of direct overlap between hybridized orbitals? This is also something that was in that notes video that you were supposed to watch within week 1 of flexible learning. So if you did not watch that, please go back and watch that first. We want direct overlap here. So those are the first types of bonds which are made. They are the stronger of the two types. They are sigma bonds. If you have something like that carbon dioxide from before, the first connection which is made in either direction, let's call it the bonds on the top, the first one made is going to be a sigma bond. They come from the hybridized orbitals. In this case, the s and p hybridized orbitals. But that second bond is going to come from an unhybridized orbital. That's going to be the pi bond. They come from the regular p orbitals that didn't change in any way. London dispersion forces and hydrogen bonding, of course, are not actually bonds. So you should have been able to eliminate those and at least got it down to a 50-50 shot. Alright, for 15. Chemists once believed that in certain circumstances, a double bond could flip between two or more possible locations. This is known as a blank structure. This would be a resonance structure. So this is similar to that example that I showed you before. I think it was with the carbon double bonding to oxygen and then going to the other two oxygens. So there are multiple ways that this structure could be put together. I could have that double bond going to the oxygen on the left, or I could have that double bond going to the oxygen on the right. And of course you would have your lone electrons going around the oxygens as well. So this right here, this would be called the resonance structure for the carbonate anion. Question 16. What happens to the bond angle as the number of bonds decreases and the number of lone pairs increases? For example, going from CH4 to NH3. So let's draw these out. So I'm going to have carbon bonding to hydrogen in 4 different directions. And I'm going to have a nitrogen bonding to 3 hydrogens. And then I have a lone pair here. So what happens to the bond angle as the number of bonds decreases? So now I only have 3 bonds, and the number of lone pairs increases. This was a fact from the notes. The bond angle is going to decrease. Now if you looked on that molecular geometry sheet, both of these are going to show up as a bond angle of 109.5 degrees because they are part of the tetrahedral family. But that is the approximate bond angle. As I increase the number of lone pairs, which are replacing the bonds which are there, the angle is actually going to decrease. So this NH3 would really have a bond angle of 107. Now, you do not have to know the actual numbers, but you do have to know that as you replace bonds with lone pairs, the angle is going to get smaller. Alright, that concludes the VSEPR practice quiz assignment. If you still have any questions, please feel free to use the weekly mailbag, or if your question is a little more personal and you don't want it to be within that open forum, please feel free to send me an email and I will get back to you.